Something has been bothering me, and I want to tell you about it. We pointed our radio telescopes at the sky starting in the late 1950s. Big, beautiful dishes, some of them hundreds of feet across, so sensitive they could pick up a signal carrying less power than a snowflake hitting the ground. And we listened. Not for a month, not for a year, for decades. We scanned thousands of stars, millions of frequencies. We built better detectors, wider receivers, smarter algorithms. We checked the waterhole, that quiet band of frequencies between hydrogen and hydroxyl radiation, where any physicist in the universe would know to tune in. We listened to nearby sun-like stars. We listened to pulsars. We did wide sweeps and targeted searches and piggyback programs that eavesdropped while other telescopes did their regular work. And what did we hear? Nothing. Absolute, perfect, dead silence. Now, silence by itself is not alarming. If I'm sitting in my office at night and the hallway is quiet, I don't worry. But imagine you're standing in the middle of a marketplace that should be packed with vendors, buyers, children running around, the clatter of carts and the bark of dogs. And instead every stall is empty, every street is deserted, every window is shuttered, the buildings are there, the stalls are there, everything is set up as if 1,000 people should be present. But nobody is. That's the universe. The stalls are built. The conditions are right. Everything is in place for a busy, crowded, noisy cosmos. And the silence we hear is not the silence of emptiness. It's the silence of a room that should be full and isn't. The kind of silence that makes you stop and listen harder because you know something is wrong. Let me show you why the room should be full. The numbers are not complicated, but they're staggering. Our galaxy, the Milky Way, contains somewhere around 200 billion stars. Some estimates go higher, maybe 300 billion, maybe 400 billion. Let's stick with 200 billion. Now, in the last couple of decades, astronomers have made a discovery that has quietly rearranged our understanding of the cosmos. Almost every star has planets. Not some stars, not the unusual ones, nearly all of them. When you look at the night sky, every point of light you see almost certainly has a family of worlds orbiting around it. Solar systems are not rare, exotic arrangements. They are the default state of affairs. Not all of those planets are interesting for our purposes, of course. Gas giants are spectacular, but you can't stand on them. Worlds too close to their star are molten nightmares. Worlds too far away are frozen solid. What matters are the rocky planets sitting in what astronomers call the habitable zone, that ring of comfortable distance where liquid water can exist on the surface. Not so close that the oceans boil, not so far that they freeze. The kind of place where if you set a glass of water on a table and came back an hour later, it would still be there. Liquid, unremarkable, waiting. Current estimates suggest about 1 in 5 sun-like stars has at least one rocky planet in this zone. Apply that fraction to 200 billion stars and you get roughly 40 billion candidate worlds, just in our one galaxy. 40 billion, think about that number for a moment. If each one of those planets were a lottery ticket, and the jackpot were the emergence of life, you'd expect someone somewhere to have won many, many times. Now, an astronomer named Frank Drake tried to make this more precise back in 1961. He wrote down an equation, a chain of fractions you multiply together to estimate how many communicating civilizations should exist in the galaxy right now. You start with the rate of star formation. You multiply by the fraction of stars with planets, then the fraction of planets that could support life, then the fraction where life actually arises, then the fraction where intelligence evolves, then the fraction that developed technology capable of sending detectable signals. And finally, you multiply by the average lifetime of such a civilization. The equation itself is beautiful in its simplicity. The problem is that we only know the first couple of terms with any confidence. The rest are guesses. And depending on whose guesses you use, the answer ranges from 0, we're alone, to millions of civilizations just in our galaxy. That's not very helpful as a prediction. But as a way of organizing your ignorance, as a way of seeing exactly what you don't know and where the uncertainties live, it's brilliant. And the important thing is this, even the pessimistic estimates, the ones that try hard to make the answer small, have trouble getting below 1. It is remarkably difficult to construct a version of the Drake equation that gives you a galaxy with nobody in it except us. The numbers keep fighting you. And the galaxy is old. Staggeringly old. About 13 billion years have passed since the Milky Way began to take shape. Our own sun is a relative newcomer. only about 4.5 billion years old. Some stars in the galaxy have been burning steadily for 10 or 11 billion years. Civilizations that arose around those ancient stars could have a head start on us of 5, 6, 7 billion years. Let me try to make that number feel real. 7 billion years ago, the Earth didn't exist. The Sun didn't exist. The cloud of gas and dust that would eventually become our solar system was still dispersed across a section of a spiral arm, not yet stirred by a supernova into collapsing. That's how far back you'd have to go to match the head start that some hypothetical civilization might have on us. Everything we've ever been, every evolutionary step from the first cell to this conversation fits inside a fraction of the time they've had. Even if such a civilization expanded through the galaxy slowly, launching ships that traveled at only a fraction of a percent of the speed of light, they could visit every star system in the Milky Way in something like 50 million to 100 million years. That sounds enormous until you remember the galaxy has been here for 13 billion years. There's been time for a slow, methodical colonization wave to wash across the galaxy 100 times over. 100 times. If you watched it in time-lapse, it would look like a drop of ink spreading through water. So where are they? Where are the artifacts? Where are the probes? Where are the megastructures, the modified atmospheres, the re-engineered stars? Why does the galaxy, which has had billions of years for somebody to redecorate, look completely stubbornly natural? The Italian physicist Enrico Fermi, one of the great scientific minds of the 20th century, first posed this question in its starkest form one day over lunch in the summer of 1950. He was eating with colleagues at the Los Alamos laboratory. The conversation had turned to a recent cartoon about flying saucers. Somebody made a joke, and then Fermi, in that off-handed way that geniuses sometimes toss out the most profound questions, said, "But where is everybody?" His colleagues laughed, but Fermi had done the arithmetic in his head. He knew the numbers. He knew the timescales, and the silence bothered him. All right, let me take you through the most obvious explanations and show you why they don't work. Because this is a detective story, and in detective stories you have to exhaust the obvious suspects before you find the real one. Suspect number 1. Distance. The galaxy is 100,000 light-years across. Our radio signals have been leaking into space for only about a century, which means they've traveled 100 light-years. That's 1/1000th of the galaxy's diameter. Maybe we simply haven't been broadcasting long enough for anyone to hear us, and they haven't been broadcasting in our direction. This sounds reasonable, but it misses the point. The question is not whether anyone has heard us. The question is why we don't see any evidence of them. A civilization millions of years old should be doing things that are visible from very far away. You don't need to receive their radio calls. You just need to notice the changes they've made to their environment. In 1960, a physicist named Freeman Dyson had a beautiful insight. He realized that any sufficiently advanced civilization would need enormous amounts of energy. A whole planet's worth wouldn't be enough, not if you're growing. You'd need to tap the energy of your star directly. And the way to do that, Dyson reasoned, was to surround the star with a vast swarm of energy-collecting structures, satellites or platforms or habitats, capturing as much of the star's light as possible. People call this a Dyson sphere, though Dyson himself always pictured it as a swarm, not a solid shell. A solid shell would be gravitationally unstable, and Dyson was too good a physicist to ignore that. But here's what makes Dyson's idea so powerful as a detection tool. The second law of thermodynamics says you cannot use energy without producing waste heat. This is not a technical limitation. This is not something you can fix with better engineering. This is one of the deepest truths in physics. Every engine, every computer, every living organism, every process that does useful work degrades some energy into heat. Always, without exception. A civilization that captures its entire star's output would use that energy for whatever it needs. Industry, computation, life support, and then it would have to radiate the leftover heat into space. That waste heat would glow in the infrared. From a distance, the star would look dimmer than expected in visible light, but suspiciously bright in infrared. It would have a fingerprint unlike anything nature produces. So we went looking. A team led by Jason Wright at Penn State used data from an infrared space telescope that had surveyed the entire sky and examined roughly 100,000 nearby galaxies. They were searching for galaxies where a significant fraction of the starlight had been converted to waste heat. Think about the scale of that search for a moment. 100,000 galaxies, each containing hundreds of billions of stars. If even one civilization in any of those galaxies had constructed megastructures on a galactic scale, the infrared excess would be unmistakable. The result, nothing. Not a single convincing candidate. The infrared sky looked perfectly natural, clean, undisturbed, as if nobody anywhere, in any of those 100,000 galaxies, had ever built anything large enough to leave a thermodynamic trace. Stop and appreciate what that result means. It doesn't just say nobody's built a Dyson sphere near us. It says nobody has done large-scale energy harvesting in any of 100,000 galaxies. The survey covered the equivalent of trillions of stars, and every single one of them looked perfectly ordinary. Whatever advanced civilizations are doing out there, if they exist at all, they're not doing anything that involves capturing starlight on a noticeable scale. Either they aren't there, they've destroyed themselves, or they've found a way to live that doesn't look like anything we expected. And there's a subtlety that makes this worse. You might think, well, maybe they only built structures around a few stars, not all of them. Maybe the coverage is partial, too faint to show up in a galaxy-wide survey. But even partial coverage produces partial waste heat. And a civilization that's been around for millions of years, expanding slowly, would gradually wrap more and more stars. The process compounds over time. Over galactic timescales, you'd expect significant infrared excess to be visible. The fact that we see none at any level in any of those galaxies is not an absence of data. It is data. It's telling us something important. We just haven't agreed on what. That finding is devastating to the space is big argument, because waste heat doesn't care about distance. It radiates in every direction at the speed of light, and it doesn't diminish in intensity any faster than regular starlight does. If somebody were using energy on a large scale, we'd see the evidence. The evidence isn't there. Dead end. Let me try another corridor. Suspect number 2, maybe life is just extraordinarily rare. Maybe 40 billion habitable zone planets sounds like a lot, but maybe the requirements for life are so absurdly specific that even 40 billion rolls of the dice aren't enough. This is called the rare Earth hypothesis, and the argument goes something like this. Liquid water is necessary but not sufficient. Maybe you also need plate tectonics to cycle carbon and keep the climate stable. Maybe you need a large moon to stabilize the tilt of your rotation axis and prevent wild swings in seasons. Maybe you need a Jupiter-like planet farther out to act as a gravitational vacuum cleaner, sweeping up asteroids that would otherwise bombard you. Maybe you need to be the right distance from the galactic center, not so close that you're bathed in radiation from supernovae, not so far out that the heavy elements needed for rocky planets are too scarce. Stack up enough conditions, and the probability drops. Stack up enough of them and maybe Earth really is alone, or nearly so. This is a serious argument. It cannot be dismissed. And there's a related idea called the Great Filter. Somewhere in the journey from dead chemistry to a star-spanning civilization, there's a step so brutally difficult that almost nobody passes it. It could be the origin of life itself. We don't actually know how life started on Earth. We have hypotheses, warm ponds, deep sea vents, but we don't have a proven mechanism. Maybe abiogenesis is a once-in-a-galaxy miracle, or the filter could come later. On Earth, life was exclusively single-celled for roughly 2 billion years. Bacteria appeared fast, within the first billion years. Then nothing much happened. For 2 billion years the planet was a world of microbes. The jump to complex cells with a nucleus, what biologists call eukaryotes, seems to have been astonishingly difficult. It may have required a very specific, very unlikely event, one type of cell engulfing another, and the two forming a permanent partnership. We call the engulfed cell the mitochondria. Without that partnership, there are no animals, no plants, no fungi, just bacteria forever. Or maybe the filter is ahead of us, not behind us. Maybe civilizations routinely destroy themselves once they develop sufficiently dangerous technology. Nuclear weapons, engineered pandemics, artificial intelligence that exceeds its creator's ability to control it, environmental collapse from industrial pollution. Each of these is a trap, and maybe most civilizations fall into one of them before they can spread to the stars. Think about it from the perspective of statistics. If a civilization has, say, a 1% chance of destroying itself in any given century once it develops industrial technology, then its expected lifetime as a technological species is only about 10,000 years. 10,000 years is not enough to colonize a galaxy. It's barely enough to colonize a neighboring star system. If self-destruction is the typical outcome for intelligence, The galaxy could be littered with the cold remains of dead civilizations, none of which lasted long enough to leave a visible mark. The silence wouldn't mean nobody was ever here. It would mean nobody survived long enough to matter. There's something deeply sobering about this, because if the filter is ahead of us rather than behind us, then we are statistically likely to walk straight into the same trap. Whatever catches civilizations, we're heading toward it, and we may not recognize it till it's too late. If the filter is behind us, we can breathe a small sigh of relief. The hard part was getting here, and we were among the lucky few who made it through. If the filter is in front of us, then our future is far darker than we imagine, and the silence of the galaxy is not just a puzzle but a warning. But here's what still nags me about the rare earth idea, even if I take it seriously. The galaxy is very, very old. Even if intelligent life arises only once every few billion years per galaxy, there has been time for multiple civilizations to have appeared. And you only need one. One successful species that decides to expand, that builds self-replicating probes, that colonizes one star at a time, slowly, patiently. One successful species with enough determination and enough time fills the galaxy. Let me drive this home with an example. Imagine a civilization that doesn't even send living beings between stars. It sends machines. Small, self-replicating machines. A probe arrives at a new star system, mines local asteroids for raw materials, builds copies of itself, and sends those copies onward to the next stars. Each copy does the same. It's exponential growth, the same mathematics that makes bacteria fill a petri dish in days. Even if each probe takes 1,000 years to reach the next star and another 1,000 years to build its copies, the entire galaxy is saturated in something like 10 to 50 million years, and the galaxy has been here for 13 billion. The math is merciless. One civilization, one decision to launch, and the galaxy fills up whether anyone else wants it to or not. The absence of that single expansionist civilization is what makes Fermi's question so sharp. You don't need to explain where all the aliens are. You just need to explain where the one nearest to us went. I've shown you 2 dead ends. Let me now turn down a different kind of path entirely. Because what if the aliens aren't missing? What if they're right where you'd expect them to be, doing exactly what you'd expect a smart civilization to do? And the reason we can't find them is that finding them is precisely what they've worked to prevent? What if the silence is not an accident but a strategy? In 1973, John Ball, a radio astronomer at MIT's Haystack Observatory, published a paper proposing what he called the zoo hypothesis. His idea was seductive in its simplicity. The galaxy is full of advanced civilizations, but they've all agreed to leave us alone. They treat the Earth like a nature reserve. They watch us the way we watch gorillas in the jungle, with fascination and care, but without interfering. Maybe they're waiting for us to reach some threshold of maturity, some mark of readiness, before they make contact. Maybe they have rules, a cosmic code of conduct, a galactic